For a do square.
Okay, this is what we're gonna do. I'm gonna check your homework, page 1 through 8 at the end of class. That way, if you need to finish it, you can finish it. But I want to spend today going over polar area. I think that's the area. I think that's maybe what is most beneficial to us, because I think you guys are probably pretty good with arc length and parametric equations. It's probably polar area that we need, the most review with. So let's see how much we can get done. From page 19 to 23, I'll walk through the steps, and then whenever we don't finish, you guys can work on some of it over break. But I'm not going to check the remaining pages until Tuesday after break. Okay. All right, page 19. Okay, so the figure shows the graph of polar curve 1 minus 2 cosine theta for theta values between 0 and pi, and the unit circle r equals 1. Find the area of the shaded region in the curve. So we know that the shaded region in the curve is, well, obviously, some parts of this is easy to find. We know that it's just this quarter circle here. Or how about this? If it's just a 3/4 circle minus whatever we need to subtract out from this 1 minus cosine theta. Okay, so basically, if we can figure out, I drew a larger version of it. If we can figure out what this area is, then we can subtract that out from the quarter circle, from the 3/4 circle, and then the remaining portion is the shaded region. Okay. So first off, though, I want to kind of talk about how this graph is moving. The graph is starting here and it's working its way around there. So this is degree 0 or radian 0 measure, and it's going to go all the way to pi. So first off, just so that we know how our graph is moving. If I want to test some values here for this 1 minus cosine theta, again, this is just a larger version of the graph, so I can just kind of explore it a little bit more. So we're starting at 0. At theta 0, my radius is -1. If I plug 0 in, I get 1 minus 2, which is -1. So that means my radius is 1. So my graph is starting here. Okay. Pi over 3 is going to go to 0. Pi over 2 is going to go to 1. That's all we need to do to figure out what we need, because at pi, it's going to go all the way over to 3. So we don't need that, right? We just need this little portion here. So again, the strategy here is the area of the shaded region minus area of shaded region is going to be the 3/4 circle area minus the area of the polar curve between the curve, the x and the y-axis. So we know that polar area always extends from the origin and it fans out, right? So the area is going to kind of accumulate from here, and it's going to accumulate this way, and it's going to wrap its way around here. Okay. So if I want to find the area of this region, it's just 1/2 integral from 0 to pi over 2, because the graph is going to start here at 0 and wrap its way around to pi over 2. 0 to pi over 2 r squared d theta. Right, so that will give me this region here, the shaded region that we see here, right? And we're kind of fanning out to create these sector regions as we go from 0 to pi over 2.
Where does the 1/2 come from?
Oh, the 1/2 is coming from the formula for area of polar area. 1/2 integral r squared d theta. Yeah, so it's good that we're refreshing our memory of. Been a while maybe that we've seen these. Okay, so, it's just a setup, right? We're not doing any calculus here. We're making the calculator do all that work for us. But it's just a setup that's the challenging part that we need to make sure we know how to do. Okay. I think that's the hardest part. I think B and C, yeah, so why don't you guys try finish part A, read part B, see if you can make sense of that. So let's spend a few minutes going through B and C, and then I'll walk through those steps. Part B says find the slope of the line tangent to the polar curve, r equals 1 minus 2 cosine theta, at the point where x is -2. So we know the connection between polar and rectangular coordinate is we know x equals r cosine theta. So r cosine theta is just 1 minus 2 cosine theta times cosine theta. Replace x with -2. We can solve this by maybe we can just do this plus 2 and set this equal to 0, and then you can graph this messy expression and look for the x-intercepts. That should get you 2.4667. And once you have your theta, then you can find dx d theta, and then build your y. And then from y, you can build your dy d theta. And once you have your dx d theta, dy d theta, you can find dy dx by finding each of the respective numerator denominator slope portions, divide them by each other to get overall slope with the x and the y components combined. Circle minus that little bit. Circle. That should work. Oh, minus. Oh, okay. I see. I put the minus. I grab and distribute it. I see. I interrelated this because I thought I assumed there was one. It should be. Yeah. It's works. It's one over here, but it's one over here. Can we? Oh, we go. Well, we go for 0 to the power of 2. So you're just doing that this sliver, right? Yeah, it should work. This should give you that. That would give you this. So it's the entire circle minus a quarter circle minus that. You have to do something with the radius over here. So this is one of that. The radius should be 1. Yeah, the radius is 1 at this stage. Oh. Let me look at how you did it and see how if I'm getting the same thing. Yeah, I'll look at it too. Keep trying it. I'll come back to that. Part C, you're finding the derivative with respect to time. See d over dt showing up. So I'm just going to find the derivative with respect to time. So r becomes dr dt, cosine theta becomes negative sine theta, d theta dt. And then if our dr dt is positive, that means the radius is going to increase. If the radius is increasing from the origin, that means that particle is moving away from the origin. Here we see dr dt is positive √3, so that's so when theta equals 2π/3, that radius is increasing, meaning the particle is moving further away from the origin. Okay, if you're good with page 19, go to page 20. Read the problem, try your steps, and then I can walk you through. Okay, 43, we just have to go through quotient rule, and then plug in theta equals 2. 44, second derivative, remember it's the formula is d over d theta of dy dx divided by dx d theta. So kind of has that extra piece when we're dealing with second derivative with parametric or with polar. Again, derivative of dy dx divided by dx d theta.
Just do DXT theta. But here you have that extra. So
The reason why is part C says particle moves along so that d theta dt. So as soon as I see time involved, I know that there's going to be another independent variable that was not present here. So I know I got to find a d over dt. So I'm going to build time into my derivative so that I can find the connection.
okay. Only if they specify.
Right. There has to be some indication as to, oh, there's time involved here for you to do related rates.
It has time involved.
Because for part C, it says d theta dt equals 2 at the top. Right, the direction gives us indication that there's time involved. Oh. Okay.
Oh yeah, it's drdt, not drd theta.
Right. If it's drd theta, then you would just do derivative like you normally would. I want to point out a problem here. This is on page 21, number 45. The idea is that normally when you think about Riemann sums, we think in terms of, oh, we're adding up areas of rectangles. But here, we're going to be adding up areas of sectors. Okay, so we know that the formula 1/2 integral of 1/2 r squared d theta really comes from the area of comes from the geometric formula of a sector region. So 1/2 r squared theta. So instead of bay times height, we're going to approximate using 4 sector regions. So instead of the change in subtracting your x values to get the change in width, now I'm just subtracting the theta values to get the change in theta. And then my r squared is part of the formula. My r is going to be coming from my second row. And I want a right Riemann sum. So that means for each subinterval, I'm going to choose the r squared for the right interval. So my theta is 1/4, my r is 4. And then it's 1/4 and 3, 1/4 and 5, 1/4 and 2. However, the formula for, it's not just base times height, right? It's 1/2 r squared theta. So we need to include the 4 squared, the 3 squared, and 5 squared. So kind of adapting Riemann sums, but for sector regions. Yeah, I'd like for us to work through page 23 so that if you have any questions about polar area, I can help answer it today because I feel like the other previous topics you guys can just do on your own. .46 is non-calculator, so see if you can work your way through without a calculator.
Get the intuition, gives the interpretation, like I don't get it logically.
So let's say we had a curve that looked like this. Right? So as we move along, right, let's say this is pi/2 or pi/4, pi/3, and then eventually the pi/2. What's happening to the radius here?
It's getting bigger.
It's getting bigger, right? So if the radius is getting bigger, that means like particles moving further, it's moving away from the origin.
But you could also like start like coming back.
Yes, right. So the idea is if I can figure out dr d theta, if I can find the rate of change of radius at that moment, I can figure out whether it's moving away from or towards.
If this was less than 0, it'd be
It'll be towards, right? That means my radius is getting smaller. My radius is getting smaller. That means the object is getting closer towards the origin.
Okay. And why does it matter if r is greater than 0 or less than 0? Oh, on the case says, because since BRD theta is greater than 0 and r is greater than 0.
Right, right. Yeah. So if r is less than 0, if r is -1, then that kind of throws things off because if radius is -1,
then it's in the opposite quadrant and things may be backwards, the radius is negative.
Wait, so if DRD theta is,
DRDT.
DRDT is negative and R is negative, then it'd be moving away.
Let's see. Yeah, I gotta think about that. That's a little bit strange because the radius is negative, then it's in the opposite quadrant. So I don't know how that works out, but I don't think we need to worry about that. We should always establish that radius is positive though. I feel like that's too many weird moving pieces if
Yeah.
radius is negative. So let's worry about radius being positive.
Okay.
For that relationship.
Okay.
Okay.
I'm just like worried, like if there's a question that's like has the right negative radius.
Yeah.
Okay.
No, but we do want to establish that this this relationship is going to be for certain if my radius is positive. So I want to let's establish that. But we won't have problems that it's trying to do DRDT when R is negative. That's too much. Yeah.
For 47, how do you know if the upper bound is?
Um. Right, instead of pi, right? I think, yeah, because there's a combination of different things here, maybe the best way to do it is just um, to graph it and see how long it takes for it to finish graphing. So let's try it. Yeah, so I went to window and I changed my theta max to just pi. And when I did that, it only showed me half the graph. So I knew that it'd be, yeah, it's either pi or 2 pi. We can quickly tell by using our calculator which one is. Yeah.
Oh, it is, well, it's not.
Right, so when I did zoom zero, it just focused in on just that, it ended right there. So it didn't finish the graph at pi, so I know that two pi is gonna be my full cycle.
Is there a way to like make a table of values on the calculator? Right.
Yeah, if you do second graph, you can see your,
Yeah, I think that makes it a lot easier.
yeah, kind of scroll through and see what's happening with each of these values. Whenever you're dealing with area between two polar curves, here's the general formula. It's you got to find the full outer area first, and then subtract the inner area. The reason why is because every area that we find has to always extend from the origin to begin with. So we got to find this full region, and then subtract the inner region, and then that will give us that remaining portion that we're looking for.
Is this a guaranteed FRQ, the polar area?
No, it's not. It tradition, I mean, from what we've seen, it shows up like every 2 years. But I mean, polar is if you look on the back here. Let's see. Yeah, I mean, polar is gonna is the third most after integration, accumulation, change, and infinite series, right? So, you know, you're going to be guaranteed at least a few problems. If you don't see it on your FRQ, then it's going to have to be there for your multiple choice. Or what happens I see is sometimes you don't see a full polar FRQ, but you see like a partial, like part C or part D of a different problem. So
It's like related rate trade, like
right, yeah, it's like related rates. Yeah, related rates just kind of randomly shows up, but it's not committing for an entire problem. So then I think if we understand that formula, 48 and 49 are pretty straightforward. Do want to touch on number 50 here. The strange thing about number 50 is that these two graphs are starting at different places. So we have R is equal to 1.25 theta. R equals to 1.25 theta, it moves in the direction that you expect. It starts at 0 and it makes its way to pi over 2 there. But R equals cosine Q2 theta plus 1, it doesn't start over here, it starts over here at 2. Because if I plug theta in for with 0, I'm going to get cosine of 0, which is 1, 1 plus 1 is 2. So it actually starts here and then moves its way here. So we got to be careful that when we accumulate our regions here, our bounds have to be adjusted accordingly. So initially, well, first off, the intersection is 0.8, so that's nice. They tell us that 0.8 is, and so from 0 to 0.8, we're definitely looking at this region here. But then because this graph is moving the other way, after 0.8, then it goes from 0.8 to pi over 2. 0.8 to pi over 2 is where the other graph picks up. So so we're not going to do 0 to pi over, or we're not doing 0 to pi over 8 for both functions because of the way that the second function is moving. If we go from 0 to pi over 2 or 0 to 0.8, then we're looking at this part of the graph, which we don't want, right? We only want the graph that is over here. So yeah, I mean, it's a calculated question, so you can see, and also even if it's not calculator, you can still create a table of values and convince yourself that this graph doesn't start at the origin, it starts over here. So technically, they could make this a non-calculator question and just ask you for the setup. You know, they wouldn't ask you to solve it by hand, but they could ask you to set it up. And I think it's good to know how to gather information about the movement of the graph by creating a table of values. Start with 0 and then choose easy unit circle values to help you see the progression of the movement of the graph. Okay, if I could come around and just check off pages 1 through 8, for you guys.
Sure. Pushed up to 29. Right?
Good.
Finish.
Okay, so you can finish that. Okay, so you're still working on page 1 through 8. I can't be patient because it was like really not good. It was like really nice and okay, I see. I just look at it. Okay. Oh, wait, not this one. The previous one. Yeah, I got it. You can just show it to you later. Okay.
I can probably show up Monday.
Okay. Oh, so you don't have 1 through 8 yet?
No.
Okay.
Yeah, and you say function, I forgot something. There's so many. I use the sure. Yeah, but you know, I use one thousand damage words like next time they do it.
Oh, you don't actually think
So I was even saying, that's good. But no, it's really easy to get outside of this. Yeah, it's the only one. It's problem.
It's actually 400 PPH from Georgia.
Like there were scandals.
Yeah. No way you might not.
I used that.
Dang, no, I used. Didn't you like show me a picture a second ago? Didn't you show me a picture like 3 seconds ago? Oh no, on Kojak.
You make art. Yeah, it's not like that. You could argue for both. I'm just like,
Bro,
I was on my business activity today where you would get.
Like-
Bro, that should be by like holding off.
I need this
the light. Hold off the light.
Yeah.
and stuff.
Like the analyst, like a doctor sees blood.
It's like
It's like the blood, like it describes like the wall and it has like two sides. It looks like there's a wall.
Okay, so just
Analyze.
Some hot is.
Straight.
Well, that's it's like like
I'm a little bit shy.
I read that.
Should I stop her? Giving you shit.
I did start
For applying. Just because like.
I didn't know.
It's the night.
Very
I'm actually happy early.
Bro.
A loss in your.
I think we did.
No, that's one.
Well, one of those.
Yeah.
It's
No, I don't want to argue. I'd rather have.
You know, I said.
You know, I'd rather have it beat you over hard.
No, I'm thinking, I'm from all this. It's a big gamble for us, like, imagine.
Yeah, that's your business.